Good evening, all. We are live now. Akash, you may proceed. Thank you.
Thanks, Asif. Good morning, good afternoon, good evening to all, and welcome to the TSTSI Tech Deep Dive 2022 conference. We are now live with the session 9 on interoperability and test beds. Before beginning with this session, let me go through some of the hygiene instructions. If attendees if you have any questions for the speakers, please type them in the Q&A tab. That's for the attendees. And you may also interact with the fellow attendees live using the chats tab during the session. And speakers are requested to kindly deliver their presentations within the allotted time durations. Reminder chime will be sounded by the timekeeper, that's me, 2 minutes before your scheduled time. And this webinar is being recorded and will be posted to the TSDSI website within the next few days. The other instructions will be made available in the chat box for the attendees. So in this session, we'll have a welcome note from the session co-chair, Mr. Subhash Mondal, and then followed by six keynotes by six experts, and then a closing address. This session is being co-chaired by Mr. Subhash Mondal from HFCL and Mr. Anand Sampatraman from TCS. Let me introduce Mr. Subhash Mundal. He leads the R&D efforts for 5G product development at HFCL as a senior vice president. In this role, he works with academia, standards development organizations, open source and technology partners. He has over 30 years of engineering experience in telecom research and development. Welcome, Mr. Subhash Mundal. Welcome, sir.
Thank you, Akash.
Next coach is Mr. Anand Sampatraman. He is the Director of Sustainability and Industry 4.0 at Tata Consultancy Services, serving Asia Pacific customers. Prior to this role, he was Head of Internet of Things for Asset and Energy Management Solutions, serving global customers at TCS. He has been instrumental in architecting and developing multiple IoT platforms and analytic models for asset and energy management solutions and providing managed services for global clients. He now consults Asia Pacific clients at TCS on sustainability and Industry 4.0. Welcome, Mr. Anand Sampatraman.
Thank you.
Now I welcome Mr. Subhash Mandal to give the welcome note. Over to you, sir.
Thank you, Akash. And good evening, good afternoon, good morning, depending on where you are joining from. I extend a warm welcome to the session speakers, indeed a impressive set of session speakers and the participants in the session on the topic interoperability and test bed. So as you know that as the network has evolved to be 5G today, beyond 5G tomorrow and 6G by 2030, the network disaggregation continues to be a driving force to enable innovation, to enable multi-vendor interoperability, plug and play, and test bed plays a very key role in stepping from the current generation of technology to the next generation of technology. So in this session, the impressive lineup of the speakers are going to cover different aspects of the interoperability test as well as the test bed to enable the research to leap into the next generation of innovation. So I would again welcome all of you and extend a warm welcome for all our speakers to enlighten us on this interesting topic. And I hope the audience will have a great learning experience from this. And any questions that you may have, we will try to answer as much as possible. If time doesn't permit, we will make sure that you are connected with the right person to respond back to your question. With that, welcome again and back to you, Akash.
Thank you, sir. So let's start with our first keynote on overview of ITUT focus group on testbeds federation for IMT 2020 and beyond. It will be given by Mr. Giulio Maguire of Telecom Italia. Introducing him, he has 30 years of experience in telecommunications, covering roles in testing, engineering, quality, and technical planning. He is the chairman of ITUT Focus Group on Testbed Federation since 2021, HC Core Network and Interoperability Testing Technical Committee since 2008, and Test Subgroup within CME Mobile User Group since 2006. He has been the vice chairman of ETSI Methods of Testing and Specifications Technical Committee from 2010 to 2012. Welcome, Mr. Giulio, and over to you.
Okay, welcome everybody. Can you hear me?
Yes, sir, we can hear you.
Okay. Okay, let me know when the screen, you can see my screen.
Yes, we can see your screen.
Okay, very good. Welcome everybody. Good afternoon, good morning, depending on where you are sitting now. I'm sitting in Rome, in Italy. So, and I'm as say the introduction said, I work in Telecom Italia, and my present role here is as a test bed federation chairman, which is the work we are doing in order to really bringing forward this topic, which is really highly important. So what we are going to see today is just a few testbed federation short introduction, and then I will give you an insight of what has been the let's say how the initiative was born between the ITUT Study Group 11 and ETSI TCINT, then the workshop that we realized that which was really a key point to start this activity, and then I will provide you some information on the focus group and summary and next step. So the importance of a federated testbed. So you know recent technology development require more realistic tests, and new use cases needs to be really validated in a real condition. And we know today we have a huge impact on privacy for the data. We have a huge impact on the security stuff. So real testbed is a must, and we need to really put together all the effort in order to create this kind of federation and interconnection of testbed. But to do that, we need to have a reference model and APIs. So uh, this was the really push for us in order to create this kind of work, in order also to give to the industry to the vertical part which need the 5G connection in order to be tested and validated, and so on. So this was the real important push for us in order to create this testbed federation group. And we start the work at CTCANT together with ITUT Study Group 11, and we produce the Q4068, which you can download directly from the link from the slides. And of course, the what has been the objective of the recommendation. The work started to define the potential improvement of the testbed interoperability, description of a reference model, specification of open API, at least the starting point, and definition of a reference metric to easy the integration and interoperability. And of course, the how do we met this goal? We made this goal because in Etsy we had a very good developed Ghana generic architecture for networking and autonomics part, which has been really for us the guide in order to provide this kind of work. And of course, we started with talking about testbed interoperability and federation. We talk about API requirement and as well and so forth. So this was only the starting point of our work, but of course was a really important step in order to start across the testbed federation. So the reference model for testbed federation. So very, very important in order to create a framework to have a open federation to API. So technical framework in order with guidelines to provide reference for developers in order to facilitate this kind of promotion. So this has been the initial work. And this kind of testbed federation has been even more, let's say, specialized because we know we can have testbed for IoT, Internet of Things, or we can have for mobile access, or Mac, or let's say core network testbed. So we have plenty of specialized testbed that we need to manage all together. And this kind of test bed needs to be federated. So in such a case, we need to work with the concept of a federation of federation, because of course in the lab I can have, for example, plenty of laboratories, that plenty of test bed, but I want to make available only one piece of that, or I have to use several of them to provide my service. And all these concepts gave to us the idea that maybe something a little bit wider than Etsy and ITU could be good to start, because at the time we had a lot of interaction with IEEE guys from US, and looking that we were working all together on the same topic. So this workshop, when we really launched this call for standardization, and we really saw the need, and a lot of people willing to contribute and come together in order to build something really fruitful for the future. And let's say when in March we had this workshop, we immediately understood that the way forward of this work was to open a focus group. Why a focus group? Because focus group, it's a way from ITUT to involve the members and not members. So anyone from organization and not organization fully. So we can involve everybody who has a real good contribution that can come to us and say, okay, this is my 2 cents on this topic. And this was important because we need to ask a contribution from APIs to be specified, to share among all the, say, the SDOs and the organization what has been already done, because this is a pre-standardization work. The real standardization work will be done in a study group 11 in ETSI INT. So here we don't talk about standard, but only technical works. And develop new business model, because I say, don't forget, of course there are maybe research and organization, state organization, but here any company we say on the market can provide its service and can get paid from the work he has done. So in this way, in December 2021, we started with Testbed Federation Focus Group. You can find more information on the web pages. And of course, all the documentation is publicly available. You have just to sign up for ITU account, and then you can access freely to all the documentation. And of course, contribution is really important, because this is a pre-standardization work, so it's created on open contributions. So the goal, harmonize testbed federation across SDOs and fora, develop the required application APIs in specification in order to align the testbed federation with the ITUT Q4068, and to try to collect use cases. And this, of course, we all the time we never say forget to say, please, if you have a new use cases you want to cover, please let us know, and collaborate, of course, with others do for research in order to provide to implement this kind of work. So the structure of the Testbed Federation Focus Group, I'm the chairman. There are Mr. Muslim El Kotob from Vodafone, who is a vice chairman. Then Ranganai from Chaparazza from Capgemini, Martin Brown from A1, and we have Sebastian Ziegler from Mandat International, Tayeb IPv6 Forum, and then Kankan Wam from China Telecommunication Corporation, and of course the advisor of from TSB Secretariat, which is Denis Andre, who is really doing an outstanding work, and really we need to thank him for all the work in supporting us and say helping in managing this kind of working group, which is really huge in terms of structure and number of participation. So we have three groups. WG1 is use cases, application in industry, and is chaired by Muslim El Kotob. Then we have a test bed as a service, which is chaired by Cedric Creta from Mandat International. And then we have the third group, reference model instantiation, which is co-chaired by Ranganai, Chaparazza, and Tayeb from IPv6 Forum. And here you have a more insight on the technical report, technical specification we are going to provide for each working group. So I'm not going into details, but you are free, of course, then to ask questions. And please, if you are interested, come and follow the Testbed Federation working group. Our meetings, we started in April 2022, then July, and now next week we have our focus group meeting, 14, 16 November. Of course, the next meeting years are not yet planned because the duration of the focus group is 1 year. So at the end of this year, we need to come back to the study group 11, say, okay, we have done all this work, but we still need 1 year to complete all the deliverable and test technical specification we had planned. So please extend our work. But let's say information will be provided quite soon. So finally, I want to wrap up what we really need. Industry needs to be really, experiment this kind of pilot and business cases in order to provide, say, real services. And Testbed Federation is a key to really enable this kind of experimentation. And we need to share the APIs and specification across companies and across organization in order to avoid to have silos, to have European, US implementation, to have a US specification, or even now, of course, TSDSI is really welcome to in this kind of work, because I realize this is a huge worldwide work, and we need to keep let's say the input from everyone in order to really try and do a good work. We need to develop a new business model because, of course, don't forget, we are here also to make business, and in order to really monetize all the effort that have been done in the sector. So I hope I just generate some curiosity in the attendance. So please come next week and join us in the next focus group meeting, which will be held from 14 to 16 will be fully virtual. So it's enough an ITU account, which you can get for free, and you're welcome. Any question? I get back to the chairman.
Thank you, Gilio, for enlightening us on the Testbed Federation. And talking about the ITUT focus group on testbed group, and also ITUT study group 11 Q.4068. Really happy to see this initiative, and I hope while in 5G time frame there are multiple test beds. Now, if the global test beds can come together to create a use case that is relevant, it would be really, really advancing the technology for the humanity in general. Thank you very much, Chilio.
Thank you to you.
Yeah. Akash, maybe we want to move to the next session. Thank you.
Right, sir. Thank you. And thank you, Mr. Julia, for the wonderful presentation. Now, to the next keynote on optical communication testbed by Mr. Atul Kumar Gupta from CDOT. Mr. Atul Kumar Gupta has more than 30 years of experience in the design and development of optical communication-based products. He has worked on design of synchronous digital hierarchy-based systems, fiber access systems, optical amplifiers, gigabit-capable passive optical networks, dense wavelength division multiplexing equipment, and quantum key distribution, etc. So I would request Mr. Asif to play the presentation.
Good evening, and thank you for this opportunity to present a talk on the optical communications testbed. I am Atul Kumar Gupta from CDOT. This is the agenda which is going to be there for today's talk. First, there will be a brief background which will be provided as to why this testbed is necessitated. What is the aim of this test bed? What are the different components inside the test bed? What sort of goals that we can expect this test bed will achieve? The block level architecture, as well as a couple of example test cases. And finally, there will be a summary of the talk. Just to give a brief background, we are all aware that the telecom industry has shifted from the voice optimized circuit switch services to data optimized packet switch services, and optical fiber has now become omnipresent in all segments of the network. Earlier, optical fiber was mostly put to use in core network where huge amount of bandwidth is required, but now even access has undergone a massive evolution from electrical to optical technologies because of the bandwidth requirements which are constantly growing. Now the DWDM has revolutionized the transport network, and the per wavelength capacity is going beyond 400 gigabits per second. The key network elements like the reconfigurable optical add-drop multiplexer, etc., are part of the core network that is getting deployed. Coherent optics is now proliferating in all segments of the network. Software-defined networking is gaining prominence. And on the access side, PON architectures have evolved and are being deployed on a massive scale. So this means that the optical communication is not limited to a particular segment of the network, but it is basically present in all segments and is getting deeper and deeper towards the customer. As far as the PON networks are concerned, we already have large-scale deployment of GPON, which is followed by other higher rate PONs providing better bandwidth and other features. So we have next generation PON, we have 25 gig EPON standards already there, and ITUT has also finalized standards for 50 gig PON. Along with the fiber-based infrastructure, we have technologies like free space optics and Li-Fi, which are gaining popularity and providing solutions where laying of fiber is not possible. Along with so much of deployment of fiber and in the and with the advancement of quantum computing, the security of the optical networks, the data which is being transported over optical networks, the confidentiality of data, that is under threat. So to address that, quantum key distribution is evolving for securing such type of communication. Now, all this background essentially is from the perspective that with so much of deployment of optical networks, optical communication modules, equipments in the network, there is a necessity to have a test bed where any indigenously developed module or an equipment or component can undergo rigorous testing before it gets proliferated in the actual network. So with that intent, we'll continue further. So basically the aim of setting up this test bed is to provide a state-of-the-art facility where any indigenously developed module or equipment is provided with a field-like environment for conducting proof of concept. Now it must be noted that while the development of many modules and equipment itself is a challenging task, the challenge gets even much more when it has to be tested for use in the existing network, which is carrying so much of data. So before any such developed technology finds its way into the network, it is essential that it is rigorously tested and in an environment which actually mimics the actual network, so that its impact on the existing services, on the existing traffic can be studied, and if there is any detrimental effect, remedial action can be taken to address those issues before network rollout is possible. So with that intent in mind, such type of a test bed is being planned, and it will support all segments, whether it is access, aggregation, core, as well as quantum security. So what is there inside the optical communication test bed is basically it will have various network elements used in optical networking. So on the access side, it will have GPON, XGS-PON and NG-PON2 with the intent to offer basically multi-vendor interoperable testing of various elements, whether it is the optical line terminal or optical network terminal, a different type of fiber, splitter, etc. Then for the core network, for the aggregation network, it will have dense wavelength division multiplexing and packet optical transport platform for testing of alien wavelengths. If there is a development which comes out with a solution which can generate a, let's say, 100 gig coherent signal, which can be used for replacing the off-the-shelf components. And it need not be just that even hardware element is there. It can be a software solution also, which requires a complete network for thorough testing. It can be network management system or a software-defined networking layer, or interoperability testing of multi-vendor DWDM or POT system. So all this will be possible using the test bed. Then it will also have a quantum key distribution solution for quantum security as well as hacking of the network to make it more robust. So all these network elements will be present to enable anyone who is carrying out development of hardware, software, component, module, etc. Rigorously. Besides this, it will also have standard test and measurement equipment like traffic generators, optical spectrum analyzers, signal analyzers for testing and debugging of indigenously developed modules. Now, one thing I would just like to add, that besides what I mentioned, the test bed needs to continuously evolve so that any further developments will enrich the test bed, so that in future, if a new type of a equipment module or a software gets developed, it is possible to test the same also. It is not a static one-time exercise. It is something which needs to be periodically revisited and upgraded. So coming to the goals, it will provide support for SDN and NMS testing. These are a couple of examples where the testbed will find use. Then performance testing under different operating environment conditions of developed modules or equipment. This is very, very essential and usually neglected part, but this is required for ensuring robustness of the developed solution. Then the network orchestration for 5G scenario, basically including this will including the slicing and other aspects which are required, particularly for rollout of 5G, the impact of the same on the optical networks. Then a couple of applications which will evolve in future, like for simulating the optical network or for predicting a fault before it actually happens, analysis of the network. So AI ML applications. So it will provide a bed for testing such applications as well. Then performance analysis of the network. This is very important. And again, if there are applications which are developed in this area, the testbed will be handy for supporting that as well. Automation for configuration and testing is another important aspect of this. And finally, testing of the network security. So with these are a couple of goals which the testbed will endeavor to meet and will be useful in ensuring that the solution is robust before it is actually rolled out. So basically the testbed will have an experimental subunit where it will be the device which is under test. It can be hardware, software, it can be fiber, it can be passive or active device. That will be the experimental subunit which will be basically tested using the communication testbed. Then there is a monitoring subunit which is actually going to monitor whatever the results are obtained from the device under test. It is going to analyze those particular results for conformance testing. And then there will be a simulation subunit which is basically going to be generating the real life testing environment for realistic testing, for giving a picture of the device under test, which can be hardware or software, whether it is up to the level required for actual rollout in the network. Going forward, this presents a overall view of the optical communication testbed which has been planned. It has the access network consisting of the PON technologies, multitude of those which have evolved over time, and it will be upgraded to newer and newer technologies as and when the same gets developed. Then it will have ROADMs, it will have CDC ROADMs, colorless, directionless, contentionless ROADMs. It will have various other flavors of ROADMs like broadcast and select ROADMs or simply colorless, directionless ROADMs. It will have EMS, it will have a layer for SDN control and orchestration, and over and above there will be a layer which will provide the quantum security. So anyone who is desiring to use this testbed will find it useful from the perspective of whatever has been developed to ensure that end-to-end testing of that is possible under all possible scenarios. So if there are any issues or problems faced during the testing, though it will be possible to debug that, because the testbed will also provide traffic generators, analyzers, spectrum analyzers, and such type of equipment for debugging and fixing the issue as and when the same is found. So as I said, this will come handy. The optical communication testbed will come handy for testing of module or network elements like splitters, muxes, amplifiers, for transceivers, be it for GPON, XGS-PON, DWDM, coherent or otherwise. Various types of ONTs and OLTs which have been developed, they can be tested for inter-vendor operability as well. New type of fibers, fiber spools, attenuators, core network elements like mux ponders or reconfigurable optical add-drop multiplexers, etc. network analyzers and network platforms, because that is a niche area. If there are network analyzers, those actually require the network for testing whether the network analyzer is working the way it is expected to be. So for that, multi-vendor interoperability of these and many more. So this is what is going to be these are some of the examples which this test bed will be able to cater. In terms of services, it can test services which are provisioned through GPON, XGS-PON2, NG-PON2, packet optical transport platform, optical transport network, cross connects, dense wavelength division multiplexing equipment, quantum key distribution, and whether coexistence on the same fiber. So the intent is again that there should be a stress testing of any developed module to ensure its robustness, and multi-vendor interoperability. Going forward, for as far as the network performance parameters are concerned, the important parameters like jitter, latency, loss, quality of service, synchronization, utilization in terms of capacity or bandwidth, availability, such type of parameters will be possible to test so that their conformance to the standards can be judged before large scale rollout. So a couple of example test cases. Let us see in case of a core network or an aggregation network, we have transponders which are, let us say, developed indigenously. So generating alien wavelengths which can be passed through the network and they can come out of a different node of the test bed, and then it can be analyzed about how they are impacting other wavelengths which are already there in the network. Besides that, it is also possible to check whether the requirements like the power level or optical signal to noise ratio or other parameters like dispersion compensation or polarization mode dispersion compensation of the alien wavelength, they are as per the expected values or not. So the purpose is twofold. One is to test the developed module. The other one is to test the impact of that, detrimental impact of that on the existing services or existing wavelengths or the existing traffic. So coming to another example, that is in case of a access network, we can test for rogue ONTs or test for multi-vendor interoperability and different fiber types. Again, the purpose is similar to what I mentioned in the previous slide, to test for end-to-end performance and not just limited to one particular device which has been developed. The next case is the performance analysis of customized network devices and algorithms. So in this case, the device under test will be subjected to different types of sorts of traffic depending upon the device type through actual fibers of different length, whatever the device is specified against, and the result will be monitored. So fiber impairments, be it result due to polarization mode dispersion, chromatic dispersion, temperature, etc., those can be measured and evaluated against the mathematically calculated or the desired values. Next case is very important, which is regarding the environmental effect simulation testing. So often this is the most neglected aspect. So the device under test will be subjected to the environmental stress. It can be in the form of higher temperature, humidity, lower temperature, or whatever. And the impact of that will be analyzed using analyzer. So this is very essential because in the field the operating conditions are different than what is there in the lab, and a developer will necessarily not have access to such type of a infrastructure for ruggedization, for testing the ruggedness of the developed solution. Another example is the testing of the different network elements end to end. You can see that one can actually test the, let's say if some new type of a ROADM reconfigurable optical add-drop multiplexer has been developed, that can be tested. Then OLT, coexistence elements for combining various type of signals, wavelengths generated by different form factor, different types of OLTs. Then the fiber or splitter, and finally with that in mind, the last item is the testing of QKD modules in the QKD network. So whether it is quantum hacking of the network, that can be tested whether it is secure against attacks, or if a new type of a QKD module is developed, that can also be tested whether it interoperates with the existing one. So that is the this one is the last example test case in which one can test the WDM PON based 5G fronthaul. This is just an example, but other type of testing will be possible. For 5G fronthaul will have its own stringent requirements, so it is possible to test the end-to-end if any solution is developed. To summarize, basically the testbed will facilitate testing of field readiness as well as interoperability of the whatever has been indigenously developed, be it a module or equipment, and this will be helpful in ruggedizing the solution and making sure that it is the right TRL level, technology readiness level, prior to rolling out in the network. So it will also help to test network performance and available service options in case of network having different vendor devices. It will ensure that any such thing is rigorously testing so that introduction of that does not degrade the existing network, and it will provide a common benchmark for testers for better network planning and management. Testbed is aimed at reducing the time to market of indigenously developed optical modules equipment by providing complete network level testing at a single place. With this, I would like to talk. Thank you very much for your patient listening, and my contact details are mentioned in this slide. Thank you very much.
Thank you, Atul, for enlightening us on the optical test bed and the plan that you are having for testing multiple technologies on GPON, XGS-PON, NG-PON, SDN, NMS, QKD, security, orchestration using AIML and other technologies for a multi-vendor interop performance and environmental testing. Thank you. Akash, we can move into the next session.
Right, so thank you for the wonderful presentation. Now let's move to the next keynote by Mr. Narayanan Rajagopal from TCS on interoperability in simulation testbeds involving co-simulation by multiple domains. Let me introduce Mr. Narayanan. He has about 30 years of experience in the area of power systems. As a principal consultant in TCS, he is engaged in building smart grid solutions, consulting and evaluation of technology and smart grid functionality for global utility customers. Welcome, Mr. Narayanan, and over to you.
Yeah, thank you, sir. Thank you for the introduction. So I will share my screen. 1 second. Hope you can see my screen now. Can you see my screen, please?
Yes.
Okay. Yeah. Thank you so much. Yeah. Primarily, I'm from the research and innovation team of TCS. I work on primarily power systems today, but I have experience earlier with industrial automation as well. And I've been closely associated with various test beds, especially typically, if you take, we could classify all of this under the cyber physical domain. And if we take the cyber physical systems, we have multiple requirements with respect to the physical models, because if you take a large cyber physical system, you have several interconnected devices, processes which are actually measured through certain sensors. So there's a flow of sensor data, and there's a physical modeling of the action which is there. Uh, it could be some of them replicated by software emulators and so on. So all of this comes together in a test bed, and we are using this uh, as a step towards uh, you know before actually a field trial could happen. So we have to evaluate. So test beds are both at a research as well as development stages are becoming important. So from that point of view, I will now look at some of the test beds that require this kind of very complex uh, exchange of information as well as modeling, and what are the basic requirements for that. So from that point of view, I would address a few elements. And one thing that comes is that there are diverse stakeholders in this type of simulations. Uh, so it could be something like a business owner, there could be a consumer, there could be a regulator, there's market, etc. Each of them looking at one side of the problem, and they all need to have at any point in time they need some kind of simulation to be run and a test bed to be evaluated. It could be a national infrastructure they could use, or they could actually have their own system but hooked up to an external system and test it. And in all of this, so design time is testing becomes very important. So even for a simple thing as like for example, uh, regulators for electricity system. So they need to look at some new policy. So they need to actually run certain simulations, right? And so all of this requires uh, a physical element of simulation as well as coordination element of multiple systems. So this has to be enabled, and all of this, if these, there is a some very highly dynamic nature of these simulations, which are actually there's exchange of information taking place. There are a lot of interactions taking place, and there are multiple domains. There could be electrical, mechanical, thermal, structural, cyber, and leave alone the communication aspect, right, between them, and multiple protocols that come in, and they have to be modeled as well. So all of this, so which actually makes it very cumbersome to weave a simulation, run a simulation, and then get the insights out of it. In terms of limitations that we have, typically what happens is there are multiple tools because there are multiple domains involved, and then there is expertise in various domains which is required. And then the hardware infrastructure and the necessary tools, and uh, typically scope of the simulation look at certain aspects in silos and ignore the other aspects. So everybody makes a siloed simulation of their problem, and then does not look at the exchange of so typically I would say, like for example, I will take the example from the electrical industry, of course, but more closer to all of us, like for example, a distribution grid. And then we try to silo the particular part of the grid, which we want to simulate, and then we do forget about the rest of the system, how it is interacting with it, and what are the communication constraints, etc. So these are the types of simulations which, and then a lot of validation waits for the field deployment of these solutions. So that's one challenge. So to be able to orchestrate test beds to run these cross-domain simulations, there are certain capabilities that have to be there. Either a large infrastructure which has a good uh, 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 good amount of hardware capability, performance capability. That's one thing. And then in a ability to also have emulate communication channels between these subcomponents. So all of this has to be there. And there is a real-time runtime component which is there, which is actually it should have the similar capability as the real world system. So that is something that becomes very important. So which actually again relates to both the model capability as well as uh, uh, the test bed hardware and software capability of the test bed. So these are the challenges that we see, and some of the needs are also arising out of this. So how this not all of it is possible at one site, and then there has to be cloud-based simulations and with the right kind of communication requirements between the system components. So with this, I would actually like to some of the test beds that some of it which is already there and some of it evolving. So from that, what are the typical architecture that they use for these kind of cross-domain test beds? So if we look at it, there are individual simulation models for each element of the system that is we are trying to simulate. So that's one part of it. And then there is a way that each of the subsystem behaves. So there should be analytics to emulate it and how they communicate. So that forms one part of the element, which is in the bottom half. So where you can see the analytics part of it, and then there can be certain physical devices that we need to verify, which can only be connected to this system and before they actually go into the field. So then the capability of hardware in the loop, so which is another element that is becomes more important. Now, the simulation models have to be deployed on some kind of target system or a PC or a server or a distributed computing infrastructure. So this is also required. And there should be a simulation manager, which actually uh, is able to configure this whole deployment. So it could be a multi-site or a single-site deployment, and then there will be communication between these elements to be able to configure the right kind of you know uh, uh, probably something like a for the Ethernet communication, and the flow exchanges could be actually controlled through some kind of flow switches for each channel of communication and so on. And then uh, individual components, how they orchestrates among them, and an overall controller, which actually controls the whole simulation. And then to be able to set up scenarios that you want to see and so on, which is actually and all of this would consume certain models, libraries, and then to be able to visualize and so on. So these are the broader elements of a typical test bed that we can look at. Uh, and when it comes to the typically one of the things that happens in all of these cyber physical systems, so if you see a device to a aggregated system or a data concentrator, there will be a certain type of communication. Let's say a LAN bus or a CAN bus or something. So this is one type of communication. Then you come to a subsystem, to a centralized system. There is another set of communication. That's one part of it, which is could be TCP/IP oriented or another type of communication. But then there is also information models which have to be you know, in each of these categories of information exchange. There will be, for example, a renewable generator or a rooftop solar has a certain information model which has to be communicated to a central system. So all of this defines the payload of that particular uh, you know uh, problem, and then so these have to be also modeled here, and often the problem is how to actually tune these information models to the bare minimum necessity that is required for the particular application. So all of this should be possible through the configuration of the communication elements. So if you see a physical system, which could be a network of physically connected components, multiple components at different places, and then each forms a node, and all of these nodes come together, and then through a communication network emulator, they come. And for each of these, and each node connects through a channel, and then for that channel, and that flow of information, what could be the bandwidth, some kind of per link, per flow, throttling the bandwidth, and so on. So this would be necessity for a good simulation environment which will actually replicate the real world. Some examples before I conclude. So I just wanted to give where this is one test bed which actually I have earlier actually we have interacted with this. There was something called a transactive energy challenge, which was done by NIST. So wherein there was a test bed. We had built some models, and it was used some small components we had built, and they were verified with a test bed, which is in Vanderbilt University, which has a co-simulation test bed, which has all of the elements. For example, if you see here, it has, because it's a energy problem. So the transmission distribution networks were modeled, the individual resources were modeled, and then each team worked on different aspects of this. The electricity markets were modeled, how consumers behave. So that was modeled. So all of this come together in this simulation environment. Similarly, the communication aspects, the sensors, so they were also modeled in this. And then what were the real-time data requirements? So that would be emulated here. So all of this done through there is a HLA based, basically this whole framework is a HLA based framework, which is a high level architecture, which is primarily defined by the Department of Defense in US, which was actually later on evolved into a IEEE standard, HLA standard. So which is what is actually used here. It The HLA architecture actually supports the federation of individual simulation components, and then information exchange, configuring the publisher subscriber architecture, all of this. So there are several in this. There were also external tools like some certain modeling and simulation tools, for example, the network model and so on, so which were also integrated into this. So it actually gives that flexibility to bring in multiple domain models, and then orchestrate a whole test bed along with that. So this was one. Uh, there's significant amount of time, of course, to put a test bed through. But then once the test bed is configured for that particular application, and then running various experiments, that itself does not take too much time. Uh, so this was one example. The other, if you see, uh, I was talking about the real-time digital simulators, so which is one part of it, and then there is because it's in all cyber physical systems, the security testing it becomes very important. So security testing by means of creating different attacks on different layers. So that being the focus, but then you need to also have the real-time emulators of the system. So this is one particular example, which is in the Iowa State University, which is we have real-time digital simulators are there. Even in India, we have in uh, people like uh, uh, Central Power Research Institute. They have, and then there is also in the chemo laboratories in Netherlands, they do have. But then extending it to the cyber physical security testing is one uniqueness of this testbed. So I thought I'll share about this. So where you have the real-time simulation, so there is a multi-area basically for power system again. So it is because my familiarity is more with power system. I'm giving power system example. Sorry, but there is a multi-area substation architecture which is actually there. There's a local as well as wide area control of this, which is actually replicated in this test system, and then uh, this is used primarily to do certain risk assessments, creating attacks, say for example, on a station level control system. So if there is an attack which is created, so what could be the impact on the network? So such kind of vulnerability assessment, how this actually could be protected by redundancy of communication as well as replicating device logics and so on. So these are some of the attack defense evaluations which are done through this. So this fairly completes what I wanted to share, but I wanted to just give a summary of whatever testbed requirements that we have seen. So as I said, uh, primarily if you look at the requirements for all these testbeds and not driving us to look at different options. So one is to be able to do cloud-based testing where it can permit, because there are certain things where cloud-based testing is not possible, where you want to see some time criticality of the order of microseconds or milliseconds. So that becomes very difficult. But certain performance-oriented or not time performance when I say, but the response time, or if that is not the concern, but how the correctness of the response and so on. When we want to see cloud-based and nodal simulation options, they really provide a good uh, method of testing. Uh, so that cloud-based test beds are that's where I think that's also allows a certain amount of collaboration. For example, universities, they could build their own test beds, but that could be for part of the system. But collaboration between universities could happen through somebody else does one part more detailed, and then he connects to another subsystem in another university or a institution. Then hardware in the loop capabilities. So this is where if real-time evaluations have to be made, so with real-time digital simulators, so this could actually give a good uh, uh, angle of performance in terms of response time and no latency and so on. Then all of these test beds, one thing that happens is often invested for a particular problem assessment, and then scalability becomes very becomes a difficult thing. So while designing, the scalability itself has to be considered. So that is where some distributed computing and architecture, so that helps. So that's where the HLA based architecture, so which is primarily helps in that. Then some specific parts have to be done in high fidelity. For example, things like power electronics, or even in terms of aerospace and so on. So where some part of it has to be a high fidelity experimentation, where the sampling times are very large, so the computing requirements are very large. So that kind of subsystems should be possible to integrate such subsystems with high fidelity experimentation. That becomes one thing. Then in terms of communication protocols, one challenge has been always there, that because it's not always possible to emulate a communication protocol in its full sense in a especially when you're looking at cyber physical systems where multiple protocols are involved. So there should be provisions actually to bring in actually some real communication gateways, where already implemented embedded hardware is there, which could be directly integrated into the system rather than reinventing the whole thing. Because then if there is simulation of everything, then it becomes if it is not closer to the actual specification of the communication protocol, sometimes even proprietary protocols are there which have to be integrated and tested. The other thing is about the information exchange models, to be able to define object models and federation of those. So that forms the important component in this simulation. So with this, yeah, if there are any questions, so I would like to take, so please.
Thank you, Narayanan, for talking about interop in simulation test bed involving co-simulation and multiple domains, cyber physical system, cross-domain simulation, simulation models, and hardware in the loop. Really appreciate your session. Akash, let's move to the next session. We're a little behind time. Maybe we'll speed up a little bit. Thank you.
Right, sir. Thank you. So, moving to the next session, which will be given by Mr. Satish Jamadagni on cloud interoperability. Mr. Satish Jamadagni is currently the Senior Vice President and Head of Global Standards at Reliance Jio, and he has 23 years of industry experience in the telecom domain. He is also the Vice Chair of TSTSI and is active in 3GPP, GSMA, and ORAN Alliance. Welcome, sir, and over to you. Yes.
Thanks, Akash. Will you be presenting?
Yes, I'm presenting.
Thank you. Can we go to the next slide? Can you go to the next slide? Maybe we can skip this. We can go to the next slide, please. Yeah. So interoperability, just as a motivation factor, there are quite a few aspects which are driving the course of interoperability as far as cloud computing is concerned. The biggest concern, of course, is vendor lock-in. That's not just the only concern. It's only when most of the departments within an enterprise or between government organizations, when they have to exchange data, that's when the problem really surfaces. So it's a fairly well-known problem, and much of what is implemented in each of the vendors may or may not necessarily, for whatever reason, technical or non-technical, may not necessarily interrupt with other data entities. So that becomes a serious problem when we go to specific use cases. We look at use cases where this becomes a problem. We are specifically talking of cloud or data interoperability. We use the word cloud or data interoperability interchangeably. And of course, that will become clearer as we go forward. Next slide, Akash. So some of the key drivers of interoperability are coming from the government side, because government has committed to implementing projects like the smart city, which of course involves data from multiple entities, data sources from multiple entities, not just data. I mean, it's even the source. And there are quite a few other private entities as well where vendor lock-in has become much of an issue. There are issues of security, because of which you would want to have multiple vendors in a single ecosystem. That's what is driving interoperability. So cloud interoperability is one of the key issues. There are multiple standards which do exist to address the overall issue of interoperability, but what do they address is something that we will look at multiple slides. Next slide, Akash. So one of the available specification is the ISO IEC 19941, which is can you make it big? I cannot see my own slide. Okay. So So the definition of interoperability is something which is a bit of which is left wanting in this specification. The objects, of course, are data. The data schema and ontologies are also something that are defined, but then not necessarily to the extent which may be necessary for specific use cases that we see in the Indian context. That's one of the reasons why it becomes imperative to look beyond the specification. Next, also, kindly understand one of the key issues why I'm just bad mouthing some of the existing specifications. And one of the simple way to bad mouth most of the specifications is the want of security. Just that one single factor alone is good enough for us to not necessarily look at some of these, or we find it wanting for the actual implementation of um, projects which are critical, especially off late when data has been weaponized. It becomes very important that any platform that is developed for the exchange of data within the context of the Indian geography is also developed within the geographic boundaries. That's one of the key issues. But of course, if you look at the IEEE NIST, I mean, they look at some of the data exchange mechanisms. But then again, there are a lot of other management issues, management plane functionalities which are not necessarily provided. But one or the other issues, I mean, there are enough things we can pick in each of these, nitpick each of these specifications. Can we go to the next slide, please? Yeah, so there are multiple other ITU specifications as well, but then obviously either they're found wanting as far as the security is concerned, or they're found wanting in terms of the generality, in terms of the implementation is concerned. There's way too much of work which has happened in terms of data patterns which are available for implementation. There's quite a bit of open source data which is available today. There's a lot of work which has happened on containers. So, this is what we want to use when we call as what we call as a platform for interoperability and data exchange within the Indian context. We need some of these flexibilities and state of the art interfaces or frameworks available to us. It becomes easier for implementation. So next slide. So in general, can we make a statement saying that no interoperability standard exists? Yeah, but of course, the critical issue here is the domain it serves, the extensive coverage that it provides. Most of them are proprietary in nature, and some of the implementation, some of the specifications themselves are left in a gray area. I mean, if you look at specific implementations which comply to some of the specifications that we discussed earlier, still found wanting because the implementation may not necessarily be fully compliant, partially compliant. You don't have a proper open source uh, libraries which are available out in the open. So yeah, this is where we start looking at trying to develop interoperability specifications for India. Next slide. So before we go any further, there's a broader issue of data privacy and ownership that has to be discussed. I mean, in the first place, it's not about interoperability. It's not just about understanding. I have a schema of data which may not necessarily be understood by the other side. It's not just that. It also is a question of data privacy and ownership. This is one of the critical factors that has to be understood if you really have to understand interoperable platforms. It's not just data translation that is something that we're looking at here. We need certain management plane functionalities which will ensure varied degrees of data privacy and ownership models. And those are something which are missing completely in the existing specification. And that's precisely where we are motivated to look at trying to develop an India specific standard. Now, what do we mean by data privacy and ownership issues? And what is the contemporary debate, both legally and otherwise, which is happening today is something that we need to look at. Next slide, Akash. So, firstly, I mean, if you look at data privacy from end user perspective, as an individual user, user of an application or user of a service which is available, Facebook as an example. Um, if you look at um, the way the model in which much of these applications work, uh, taking the example of Facebook today, Facebook is free primarily because you're giving them a tactic, under a tactic understanding, you're giving them the right to use the data that you generate. The user data is completely within the domain of the application service provider. What that means is that they can play around with data. They can run analytics tools. They can crunch the data to extract whatever nuggets that they can pull out. But that is the whole understanding, a tactic understanding, though not everybody goes through 900 pages of legal documents which they put in front of you to sign up. That's precisely what happens as far as the privacy concerns are concerned. So that is as far as the end user is concerned. It works. It sort of is working as far as the Facebooks and the Twitter and rest of the social media application space is concerned, because primarily they use your data. That is not something which is acceptable in the enterprise domain. I mean, it's not even acceptable in the end user case, and that's precisely what the national data localization and that national data policy is all about. I mean, it's not just localization; it is also about what entities can do as far as the data generated by people of a nation is concerned. So, one of the examples is this is an ongoing case in Supreme Court. The government lawyers are arguing that you cannot have non decipherable systems coming into the country and pulling out data wherein you don't know. The government has no clue of what's happening. I mean, of course, one of the biggest claims is the security concerns. I mean, this is something which is valid. There are instances of multiple levels of privacy violations. Anyway, so anyway, that's an ongoing discussion. But essentially, when it comes to the enterprise domain, this tactic understanding goes away. That means an enterprise, the data generated by an enterprise belongs to the enterprise, and the enterprises want a mechanism before even we talk of any collaboration or interoperability or any such thing. We want to have a platform where we're ensured that not we can safely share data, one part of the story, but then we also have the appropriate management plane functionalities implemented where we can monitor and enforce a certain level of rights on the data usage. I mean, just because you have access to my data does not necessarily mean you can run any kind of analytic tools on top of the data and pull out some juice and then try to sell it somewhere else. I mean, these are the nitty-gritties of legalities. But then you need an enforcement tool, and that's precisely where the platform comes into the picture. This has to be built into the specifications and into the platform. So this is the broader debate, broader argument under which we look at the cloud interoperability specification being developed in India. We'll go to the next slide, Akash. Let's take an example. Um, let's take an example of smart city. It's a very intricate, a classic example where you have way too many entities which own data, which generate data, which consume data. You can have a so-called IoT service provider who provides an IoT communication network with all the sensors and the data um, collection capabilities. Then he may not necessarily be the entity which will use it. And in the broader picture, when you implement something like this, you'll also have old records, data, which is just simply taken away from, it's simply scanned documents of papers. You also have satellite data, which comes in certain formats. You have drone services, essentially, which can come at multiple levels of metadata, degrees of metadata. So you have a cloud service provider. You may have AI analytics service provider, independent of all this stuff. You can also have an application service provider. The way they interact to make sure that there exists a broader goal of smart city, and that's the most tricky part. So here, if you look at this classic example, you have data getting exchanged, multiple parties. The owner of the data is somebody else, the user of the data is somebody else. There are certain departments like traffic monitoring and other departments which also are sensitive. You may not necessarily want to share this with the general public, or pollution control or some such thing. It may be used for this. I'm talking of real time data. You have a gross, data of what the pollution levels are. That those are perfectly fine. But then the final levels of data is what we're talking about. These are not something that enterprises will be willing to share, or even if they do share under some agreement, they want to have mechanisms where the other party, they can ensure that the other party is using the data in the appropriate format that was intended to, as per whatever agreements there may exist. So this is a broad picture, and this smart city is a classic example where multiple of these entities exchange data, and there's a federation of, or a hierarchy of management rights which needs to be enforced. You need a platform for that. So that platform essentially forms a cloud interoperability platform. That's precisely what we intend to um, cook up and publish. Next slide, Akash. The same smart city example. You have multiple levels of entities involved in trying to bring about a complete solution as far as a smart city is concerned. IoT is another example. You have agri-tech is another example where multiple entities are involved, and agri-tech is a very sensitive area where it's very easy to talk of, okay, I can deploy IoT to bring about a lot of changes as far as the agri-tech is concerned. But how do you make sure that the data is not falling into the wrong hands within the ecosystem? I'm not even talking of being hacked and somebody pulling out your data. I'm talking of within the ecosystem of interoperable entities. How do you make sure that the data is not falling into the wrong hands? Because the agricultural data can be manipulated big time. There's also the commodity trade market, which is very keen to get such data. So obviously, these are something which everybody is keen to protect. So there is a certain amount of certain functionalities or demands of feature support that comes on the platform, which claims itself to be a cloud interoperable platform. Next slide, Akash. So when we design a cloud or a data interoperability platform, you must understand, when we talk of cloud interoperability, primarily it's a data interoperability platform. Though we keep using this cloud, subject to the ability of how much of management plane plus security plane functionalities we add in. It's either simply data interoperability platform, or as you make it complex, it becomes, one can call it cloud interoperability platform. So how can one go about with designing a cloud interoperability platform? There are a lot of data management patterns which are available today in the literature, in the state of the art, open source. It's available. So, given the set of requirements that we have, we can. It's very easy to look up certain of the data management patterns, or even other patterns, control patterns, which can be used to design overall cloud interoperability platform. Next slide. So I'll just give a couple of examples of what are the kind of patterns that we can use.
Satish, sorry for interrupting. Please speed up a little bit. Thank you.
Okay. So we have the broker architecture. What a broker architecture does is primarily provide some APIs, which can be used by consumers of the so-called API. It can either be API aggregated or may not necessarily be aggregated. API aggregation itself is a pattern. If you look at it, here we are assuming that most of the applications which will be deployed will be microservice-based application, but it may not necessarily be. I mean, you always have an API interface or a API aggregation set which will be exposed as part of a specification, which can be used. Next slide. Different models of deployment for cloud interoperability. I mean, where you have the interoperable gateway sitting in. Next slide. So there are other patterns as well, which readily sort of fits into the scheme of things that we are looking at as far as what we could call as a cloud interoperability pattern. One of that is called as a saga pattern. I mean, if you're in the field, you would know what this is. So what it does is, if you have distributed huge number of transactions across multiple entities, it sort of streamlines it, gives you a readily available structure as to how the exchanges can happen and how the synchronization happens, and you're not left wanting on either the data plane or the control plane. Next slide. So in general, what happens is, this is the broad outlook. I mean, we are looking at a very high level architecture. Of course, there are a lot of nitty gritties which happens. You have an API gateway, and anybody who wants to talk to anybody on the other side will have to come through an API gateway. But then the API gateway will have to implement a security plane, a management plane, a control plane, slash control plane, and a data plane. Of course, data plane will also have to have some kind of a mesh, data mesh. I mean, essentially a data translator. Data mesh is also a pattern. Those are the ones which it will have to implement. So broadly, we are giving tools. What I'm just flashing on the screen is a bunch of tools which can be used to develop cloud interoperability platforms for the set goals that was discussed earlier. Next slide. Just taking an example of 3GPP, 3GPP can also be a carrier of multiple of these smart city or IoT or any of these platforms. Then the 3GPP architecture gives you something called as service communication proxy, which in itself is one of the entities within the grand scheme of things. But this is something which already implements a certain amount of microservice kind of an architecture which can be used. But then again, of course, you will have to still enforce a lot of APIs on top of it for a given set of use case. Next slide. The same thing. We'll go on and trying to. Security is another key issue, which is security is another key issue which will have to be covered across the board at multiple levels. So whatever is given here, essentially, you need to have security across data plane, control plane. So when we call of something called as a security plane, it is quite intertwined with the management slash control plane and the data plane. So this is as much as the broad scheme of things that the cloud interoperability is concerned. This is an ongoing work in TSDSI, which is expected to be completed very soon. Next slide. Okay, done. Thank you.
Thank you, Satish, and sorry for rushing you. I know it's a big topic. Cloud is really in cloud, so thank you for covering different challenges, specifically with the data privacy, data ownership, and way forward that you potentially can look at different architectural pattern. Thank you, Satish. Akash, maybe we can move to next one quickly. We are little behind schedule, so let's move little quick.
Right, sir. So moving to the next keynote, it's on. Yes. Sorry, screen got froze. So the next keynote is from Mr. Anand Sampatraman, who is also the co-chair of this session. Let me request Mr. Anand Sampatraman to take over. Thank you.
Thank you, Akash. I'll share my screen.
Yes.
Please let me know if you can see my screen. I'll get started.
Yes, it's on now.
Thank you. I think I was kind of feeling happy when Mr. Satish was touching on from a smart city, the challenges around interoperability and many such. I was actually wondering if my presentation will be from a very different context than the earlier things that I saw. Having said that, let me kind of take possibly a different perspective, which probably is from the vantage point where I work from TCS. The way we see the world adopting to digital transformation uh, is in the context of how are enterprises forming their ecosystem, how are they extending their enterprise ecosystem through their value chain, both their upstream and downstream, and how does such enterprise value chain covering the value chain gets extended to what we see as a cross industry ecosystem, and finally cross sectoral ecosystem. This is a kind of trend that we see emerging thanks to the cloud adoption, probably seen as a progressive evolution. The way the world is probably moving towards what we see as a data platform economy. Having said that, probably a couple of examples to say. It can be in the context of, say, smart buildings. It can be in the context of distributed energy resources, integration of diverse resources across industries. So that said, we see this as a natural progression that multiple sectors will take, probably even can be seen at a country level. And having said that, needless to say, it all hinges on cybersecurity for sure. We all know that cybersecurity is a challenge. However, interoperability certainly becomes a huge challenge, right? When you kind of bring such diverse ecosystem together. So that's where, if these ecosystems leverage the emerging technologies, and we all know that these technologies have already come to life, right? Cloud is there. Whatever data technologies are already showing great promises. You call it AI, you call it IoT and blockchain, you call it digitizing operations or products and services. There are several consumer centric industries which have already proven that the art of possible is there. Having said that, if these enterprises have to leverage these emerging technologies, how do how do we see the need for interoperability, right? Interoperability needs to enable what we see as value chain orchestration. Needless to say, data privacy, protecting the data of various stakeholders, various organizations participating, whatever entities participating, becomes critical. Second, when platforms are kind of conceived, and if they want to kind of democratize data, federate data in their means to monetize, how is that going to be enabled? And how are cross industry platforms going to enable collaboration, right? And I think we all know that open APIs have come. One of the earlier speaker, I think Mr. Giulio, was addressing about how test beds can be federated, how can open APIs kind of be embraced in the context of such integrations. Having said that, today the hyperscalers are advocating several such philosophies. The data structure, data schema that the hyperscalers are embracing or advocating. On the other side, we all know that every industries have their own set of standards, right? Standards that are being advocated layers of these solutions. So how are interoperability challenges bringing together these various, be it automation vendors, be it the OEMs, how was that going to be enabled? And when you do that, definitely data privacy and security are going to be extremely important, be it specific to a country, specific to an industry. How are those sensitive data going to be protected, confidential data going to be protected? How are certifications going to be enabled between the various networks that participate in all of this? Will be of significant importance. And all of these are going to determine the rate in which it's going to be accepted, also, right? And finally, standardization, be it API standardization or standardization of industry data models. That's going to be another critical factor, right? That's where comes in the importance of what we call as common information model that industries are wanting to establish. There are several initiatives already that we see globally. One of the initiatives which many of us may be aware of is one that the energy industry is adopting, right? The OS2 platform, which is significantly seeing probably more than 200 partners coming together today, or 200 ecosystem coming together to establish possibly a platform which can be embraced across energy industry use models. So standardization will certainly become key. So if these can all be brought together, possibly there is going to be a solution going forward. And when you have such solutions being conceived, some of the key themes that we see is going to gain importance. We all know the technical dependencies that it will have in terms of the architecture in which data exchanges needs to happen. However, even important is going to be from a business perspective in terms of how are you going to even kind of bring these uh, various stakeholders, right? The stakeholders are going to be not only the community, the consumers, there are also going to be regulatory stakeholders, there are going to be various digital partners are going to participate. And we know security and legal for sure are going to be important. Regulatory enablement is going to be important. Finally, from a solutioning perspective, it's going to be all around semantics, right? How are industry semantics going to be appropriately defined? How are metadata going to be appropriately established? What is going to be the right taxonomy for, be it at industry level or at a sub industry level? How are you going to link data coming from these diverse systems, establish the right ontology taxonomy, have this enable the kind of innovative use model that you're going to see? All of these, I'm sure, have to be given due consideration if we have to establish that interoperability, what we call as the information and data governance related to all of this, is possibly something to be given due consideration. Having said that, a quick view of a sample information model, right? We are talking about by again, it's kind of meeting all the use models, but what we see fairly working, and at the same time it also have limitations when it comes to handling data privacy, when it comes to handling uh, some of the innovative use models that they want to try, is kind of calling for this level of complexity. This view is to kind of give uh, the various stakeholders a view of the kind of complexity that it comes for an information model, right? And this is the sample that I've chosen here is for smart buildings. Smart building, it kind of calls for 12 layers of data or a dozen layers of data to be brought together. And each of these layers are going to have several partners, right? Several product providers, several OEMs participating. And if we have to bring these together, bring them to the appropriate semantics in the legal framework with the right technical architecture, which will be performing at the on one side is performance requirement, on the other side is commercial requirement, right? I think there's enough of challenges to be addressed. And having said that, taking another view to look at the same problem of interoperability, while we saw it from an information model perspective, if we have to see it from a data marketplace, right? One of the theme that we see emerging is enterprises are looking to democratize data, and through democratization wanting to monetize data, and wherein enterprises are conceiving what we see as a data marketplace. And all of these data marketplaces have disparate systems and technologies to be integrated. You call it whatever data sources and different data types that you can think of. These data can be brought together, right? Bringing data, integrating data, bringing data probably is a challenge solved. But when you bring them with the appropriate challenges of data semantics, right? Establishing data between the various systems and subsystems, getting them to have the right grammar, getting them to be relatable to the other systems, and in that process, ensuring data privacy, ensuring security, all of that. I think that's the real challenge I'm sure we are all trying to address. So data marketplace is another view. And finally, if I have to put a data hub kind of an architecture, which typically what hyperscalers are kind of advocating for, and this can be seen from any industry context, right? Or rather many industry contexts. If we have to bring that data from the various assets, whatever be the operational considerations, and if we also have to bring in the various partner ecosystems, and if we have to kind of bring in the community or the consumer stakeholders, and all of these have to be orchestrated, architected on an hyperscaler environment, I think if the challenge around interoperability, giving due consideration to data privacy, cybersecurity is addressed. And this is going to be a huge breakthrough. And here comes the additional advantage, or I don't know, should I call it as complexity or opportunity? If technologies like 5G is brought in, uh, I think there's going to be huge opportunity space for innovation if only these interoperability problems are appropriately addressed, and if there can be a simpler way to address, and if there can be adoption finally from the industrial community, I think that's going to be a great way to go forward. So what you see, or what you have seen, is from a data perspective, from the way the world wants to go, from the way the industrialization will want to embrace, having adopted cloud, move towards a platform economy, move towards bringing together the various value stream of data, orchestrate for the newer insights intelligence. We definitely see that as a way forward. With that, thank you. We'll be happy to take questions. We'll be happy to reflect along with the other speakers on the various test beds that they were all advocating for. Thank you. I hope I was quick and
Yeah, thank you, Anand. You are on time. I really appreciate that. Thank you for sharing your views on the role of common information model that really can help create a multidimensional interop need in a digital economy that we live in. You talked about quite a few interesting stuff: data federation, cross industry, cross platform collaboration using a common information model. So really appreciate you sharing the views. Thank you. Yeah,
thank you.
Akash, next session, please.
Right, sir. So the next keynote is from Dr. Rohit Budhiraja from IIT Kanpur on design of indigenous 5G cellular network. Introducing Dr. Rohit, he is currently an associate professor in IIT Kanpur, where he led the effort to design the indigenous 5G network. He is also currently leading the 5G and beyond standardization project from IIT Kanpur. Welcome, Dr. Rohit, and over to you.
So, am I audible?
Yes.
Okay. So can I share my screen?
Yes.
Okay. Is my screen visible?
Not
Not yet.
yet.
Let's check it again.
Sir, can you click on the present audience, then select the portion by selecting entire screen and all?
Yeah, that's what I'm doing. This is- Okay. Seems to be an issue. Okay. So, Akash, can you share it?
Yes, okay, I'll share it. No problem.
Okay. Yeah, I'll start by thanking TSDSI to invite me for giving this talk, and this is about this indigenous 5G network which we have designed across institutions. So I should thank DOT for funding this project. It was a 3-year project funded by DOT, and the objective was to build and demonstrate an end-to-end 5G network, completely indigenous. Hardware, software, everything had to be designed from scratch. So that was the idea, and that's how we started in April 2018. And I'm happy to say that we've actually achieved that objective within the stipulated time. And you might be aware that we recently demonstrated call over this 5G network also. So let's go on and see what we have developed in this project. So next slide. So institutes which were involved in designing these 5G network were these 5 institutions: IIT Kanpur, Madras, then IIT Bombay, Sameer, then Center of Excellence in Wireless Technology. So 15 investigators, which were like faculty members, senior researchers from these 5 institutes, and 150 employees who were working on this, building this test bed from scratch. So that's the kind of effort it was. And when we started, as I said, the mandate was to design an actual product, not a lab technology demonstrator. Usually in academic project, that's what happens, that the technology remains in the lab, but our intention was completely different. So we have demonstrated an actual product. So and the idea was to like build this network for both sub 6 gigahertz and millimeter wave band, and to design it for the bandwidth supported in these 2 bands. And if we are aware that the sub 6 maximum bandwidth available is 100 megahertz, and millimeter wave has 400 megahertz of bandwidth, so which 5G supports. So we have designed our network to cater to both these spectrums. So next slide. So if you look at the kind of network which we have designed, is basically we have divided this into basically broadly 3 nodes. Okay, so if you look at it, the first node is the remote radio head, and which radiates the signal which you see on tower tops. So this is the radiating part of the network, but the complete processing is done in the baseband unit, which is the heart of this 5G network. Okay, which like does the complete processing of all the signals. So the signals from the remote radio head are basically digitized and brought to this baseband unit, which runs all the algorithms starting from physical layer, MAC layer, and then upper layers also. Okay, so all the processing is done in baseband unit, and finally it is connected to the core network, which for a layman it does authentication, and then security. It does billing, so it does all this. So this is how this 5G network is architected. So if you look at this, so broadly 3 nodes: the remote radio head, the baseband unit, and the 5G core. Each one of them has its own tasks. And if you look at it, the way we have this whole network was designed across 5 institutions. So I'll just show what each institution did. Next slide. So this, if you look, so the remote radio head was designed across these 2 institutions, IIT Madras and Sameer. The baseband unit was designed in IIT Kanpur. Then the 5G core was designed in IIT Bombay and Civil. So it is a nice example of how multiple institutions can work together and deliver such a complicated technology. So and the UE is basically is commercial UE. We have not done the UE part over here. So it talks to a commercial UE. When we talk about making a 5G call, so we have our own homegrown network, of which the complete hardware and the software was developed across these institutions. When I say IIT did the baseband, it essentially means that we designed the hardware, complete hardware in-house. I'll show you that also. Okay, but that's how we have done it. So everything except ICs, everything was done across these institutions. Next slide, please. So this is a brief overview of how we have architected this baseband, which, as I said, is the heart of this 5G network. So if you look at in any wireless network, there are multiple layers, and each layer has its own task. So the bottommost layer is basically the physical layer, which is which does time critical processing, and that processing is done in dedicated process. If you see channel coding, scrambling, these are basically physical layer tasks, very, very compute intensive. Okay, so and we built a hardware to enable this time critical processing. So this is that hardware which you see on the right hand side, which was built in IIT Kanpur. to enable that time critical processing of this physical layer signals. And it is designed, this hardware is designed such that it interfaces to a general purpose server through the PCI interface, so that all the other layers, RRC, the PDCP, which is radio resource control layer, packet data convergence protocol, RLC, MAC, all these layers are run on a 8086 server. Okay, right? So so the architecture broadly is physical layer on a homegrown hardware, which runs critical physical layer processing, and the other layers run on a 86 server, and these two are interfaced using a 64 gigabit PCI interface. And this baseband unit has to be connected to the remote radio head which radiates the signal. So you see this is a 40 gigabit optical interface which connects it to the remote radio head. So I'll show you how remote radio head is architected. Next slide, please. So you see this, the remote radio head, go back. Yeah, so the 5G is about one feature of 5G is, if you look at it from the network perspective, installing a lot of antennas, okay, so which basically helps in reducing the interference across cells. That's what this massive MIMO technology is. So we have also built our this remote radio head with 64 radio frequency chains. Okay, so if you blow it up, so you look at this, there are like so there are 4 different boards, okay, which each of them will serve are designed to serve 16 RF chains. So 4 such four such boards, which make it a 64 radio RF chains, okay, and then they talk to a centralized card. This is called data aggregated card. Okay, so you look at this is the block diagram, 16 chain per board. So 4 of them make 64 chains, and all of them communicate to this data aggregator. This you can call it as a motherboard. Okay, and from there the data is taken to the baseband unit, which I showed you in the last slide. So look at the complexity of designing it. So this was done at IIT Madras, okay, and so it was architected so that the remote radio head can talk to baseband unit over this ORAN interface, which is a standard industry interface, and that's how we have architected. It's like all other networks are also architected in a similar way. So ORAN is a standard industry compliant interface over which these two subsystems communicate with each other on an optical link. Next slide, please. So as I said, the agenda was to build an actual product. So if you look at it, that's how the baseband unit looks like. Okay, so this is how the card fits in. As a PCI card that fits in the motherboard. Okay, and these are the features which this baseband unit supports. Supports 256 QAM. It supports 25 users per 0.5 millisecond. This is TTI duration. Has support for MIMO, and it has a PCI form factor so that it can fit in a general purpose server. Okay? And as I said, it is designed such that it talks to remote radio head over ORAN interface. So again, as an industry standard interface. So next slide, please. So this is different forms, different avatars of the remote radio head. So we have designed for different antenna configuration based on what an operator demands. So this is what I'm showing you is for sub-6 gigahertz. It's FR1, and for FR2 the design changes. So we have done the design, and even so the hardware is available for millimeter wave remote radio head also. The baseband unit remains same for both FR1 and FR2. That's how we have architected it. So the baseband unit can support processing of 100 megahertz as well as for 400 megahertz. Okay, so so the remote radio head is available with 16 antennas, 32 antennas, and 64 antennas. So transmit power changes accordingly. Okay, So 16 antenna has a transmit power of 56 dBm, 62 dBm. 32 antenna has 62 dBm, and 64 antenna has a 68 dBm transmit power. Okay, and the correspondingly the weight changes. The key thing is like that they are as close as it can be to the product. So the technology TRL, we claim that our the subsystem has a technology ready level of 7.5. Next slide, please. So that's how the complete indigenous network looks like. This is the remote radio head. This is the baseband unit. This is the optical interface. This is connected to the core network. And over a normal Ethernet link. And it communicates to the user equipment. We recently demonstrated this end-to-end network. Next slide, please. So these are the few demos which we have done. It was showcased in Indian Mobile Congress. It was showcased in IIT R&D Fest, and we are talking to companies for the technology transfer. Next slide. So I'll spend 2 minutes, and after that I'll wind up. So how 5G network is being used in the labs. So next slide. So it can basically, the different applications can be brought in which can use this test bed to connect. And this is an end-to-end network with a core network. So any application can be brought in and can be tested over this network in the lab. So next slide. Then if this is like, in principle, it can be done if there are the students and scholars who actually want to get down to testing their algorithms. They can also test it. Like, as I said, everything was done in-house. The algorithms, the hardware. So some part of the algorithm can be modified so that students can check their algorithms, like the baseband part, the physical layer part can actually be replaced by the algorithm written by the students. So that can also be done, but it has to be done in a specific way so that it interfaces with the algorithms which we have designed or the system which we have built. So the usage of this test bed or the network are unlimited, and it is, as we talk, there are companies who are using this network to test their applications. So next slide. So our effort was recently appreciated by Honorable Prime Minister in his last Mann Ki Baat. So if you can play this video, it will be nice. If you're not able to, then also it is fine. I cannot hear it. I cannot hear the sound. It's okay if you're not able to hear what Honorable Prime Minister, he appreciated the efforts put in by IITs to develop this fully homegrown network. So I'll conclude my talk. So this is like the 5G network, which was completely built from scratch in-house. Other than the IC, everything was done. So remote radio head, baseband unit, and so UE hardware and software was also built, but the one I showed you did not involve this UE hardware and software. So core network was also built in-house. And next slide. It is extreme hardware engineering. We did like sitting in these institutions, sitting in these labs. They're mostly done by students or master's students or PhD students who work on building these hardwares. Of course, we had the experience personally. I had the experience of building such networks before. So we guided students to build these networks, and so we have achieved that. So extremely dense hardware with like such high-speed interfaces, and so we have built this hardware for both millimeter wave and sub-6 gigahertz. Extreme hardware engineering and software engineering, which we have achieved. We have trained around 200, 250 students to build, who have worked on different aspects of these networks. I'll stop by now, like, with this conclusion. Thank you.
Thank you, Professor Rohit Budiraja. Really appreciate you sharing the inspiring journey of India in creating technology test bed, the real product, in an academic setup which is originally intended to do the academic research. So it's an inspiration for all of us to take
Thank you,
this
sir.
forward and then create the indigenous product. Thank you very much.
Thank you. Thank
Chair, with your permission, there are two questions
you. Sure.
addressed to Mr. Dr. Buddhi Raja.
Yeah. Yes.
Sif, can you? Yes.
Yeah, so I will see. I'm not the one who works on core, so I can guide. I can connect you to one person, but prima facie, it looks like it can be tested on the 5G core part. I don't work on 5G core, but I can. Like there are companies who are who've been testing using this core network also. I can connect them to the person, to the relevant person who can answer this question.
Akash, next question. Yeah.
Okay, again, so I am on the network side, I'm not on the application side. So I'll not be able to answer this question. But the thing is that writing an application should not be different for a 4G or a network or a 5G network. This is it comes from my limited understanding. Because the network will actually provide you high-end link to connect to the network, to connect to the network, okay, or to the internet. It doesn't change the way applications are written. It will enable those applications which require these kind of high bitrate connections, okay, like virtual reality, right? Cars or ultra reliable low latency communication. So it will enable that. I don't. So if you have to build such applications, the design of these applications will change. But overall, how you write these applications, I personally think that's not going to change. That's based on my limited understanding. Okay. And as I don't work on the application layer side, that's how I would put it.
Maybe I'll quickly add just 30 seconds to your response, Budhiraja, if that helps that participant. So if you are really looking at the common API framework that 5G has exposed and the MEC APIs that 5G has enabled, which is 5G MEC APIs are not fully standardized yet, though it is in HC, MEC has been fairly mature. There is a possibility of you hosting the application in a standard compliant way. So if you are looking at getting into the edge computing with a local breakout at UPF and accelerate your program, there are potential for you to do. But rest of the thing that Dr. Budhiraja talked about in terms of application programming, perhaps nothing changes. But instrumenting your server and orchestrating the services in a way that accelerates the end user experience, there are opportunities. So with that, I will pause. And if you need any discussion subsequently, I'll be happy to connect you to the right people. Thank you.
I think there is one more question. That's what.
Shall I flash it, sir, on screen? There is one more question in chat tab.
Yeah, please.
So what is the status of TOT? Okay, we have been talking to companies and they've shown initial interest. Then still, I mean, we hope that it will happen. Okay, I cannot really we are talking to companies and they have told us the technology transfer will happen. Yes. So unless until there is, I have a written commitment from that, then I cannot really say that it will happen. But we are very close. That's how I would put it.
Thank you.
No more questions, sir.
Thank you. Thank you for giving me this opportunity to present our journey. Thank you.
Thank you. Akash,
Right, sir. We have covered all the questions that were addressed to this keynote. Now, the next keynote is by you on Open RAN opportunities and challenges. So, over to you, sir.
Thank you. I'm trying to share my screen.
Yes,
Is
it's
my session.
online.
Is the presentation mode showing up, Akash?
Yes.
Good evening, and thank you for staying late. I know I'm the last in the session speaker, so it's already late. We are delayed by 20 minutes. So I'll try to wrap it up in 10 minutes if possible. So whatever I am sharing on the Open RAN opportunities and challenges is based on my experience for our last 1 year in building a Open RAN product. So we are creating a 88R macro radio, 40 watt per TRX category, both category A, category B features we are implementing in ORAN. So some of the opportunities and challenges that I will share from my experience. Uh, so I'll very quickly talk about the what are the opportunities and what are the challenges. So as you know that why open radio access network came to the prominence is really for removing the vendor lock-in, something that Satish had talked about. Freedom to choose across suppliers, create a concept of build your own network, open interoperable interface to enable truly multi-vendor network, open up the intelligence and reduce OPEX and CAPEX and optimize the total cost of ownership. Now I look at it as a breaking the system is the primary motto. So I have taken that human body as an analogy. If you really look at it, we have a central nervous system interconnected by a transport network, and then you are having a set of actuators that is activating you to respond to the responses that we are getting. So the loose analogy to that is the central nervous system is the core network, the I'm sorry, the your brains is the core network, and then the your transport is happening. All the sensory thing is getting transported through your uh, uh, the spinal cord, and then you're having your arms and legs actuated through this, right? So if I move into the evolution of network technology, the brain is the core network. Of course, it is distributed also to the radio access control functionality in the RAN. And the RAN and core are reasonably standardized in 3GPP. And transport network, of course, is outside 3GPP. But the attribute required to mobilize the 5G network, for example, in collaboration with IETF standard, it is reasonably defined in terms of the quality of services required from transport point of view to meet all the quality control categories that is required in the form of a QCI. So the last frontier that was left out from the standardization perspective, something that Dr. Budiraja also talked about, is the further disaggregation at the radio last mile, which is in 3GPP you have the CU and DU defined. RU is part of the DU, but when you come to Open RAN, you essentially open up the front haul also and give a connectivity. And then 5G network has given the utility to create the private 5G, public 5G, and then depending on the deployment model, you really can orchestrate things in such a fashion that you can seamlessly work between private public network, and also at the same time you leverage the enterprise network, which is typically last mile distributed over Wi-Fi. And all the services could be mixed subject to the quality of service requirement. You can integrate both licensed and unlicensed technologies together. So a lot of opportunities are opening up there. But I specifically will talk about the Open RAN. So if you really look at it, something that I refer to is that the real complex work has happened in the front hall, where the RU is separate out from the DU. So essentially the key information in the form of I and Q symbols that is required when you split the physical layer, carrying them and making sure that their information integrity is maintained, and you still can effectively distribute the function and then make sure that the end-to-end functional integrity is not broken. Of course, it has other interfaces like the open frontal management plane interface, open frontal O1 interface that allows a seamless orchestration to create the near real-time and non-real-time optimization opportunities that are earlier not that easily accessible. So because it was a vendor specific intelligence, now this gives the opportunity to open up. So these are the opportunities that open radio access network is bringing in. However, there are challenges. Just to give little bit of a view of ORAN split 7.2 X, which is the EC-PRE interface where the low-fi, high-fi are distributed, and this is an option that we have implemented in our product. So if you really look at, there is a huge data rate that is required between high-fi, low-fi. Of course, 7.2x is the minimum data rate you can do. If you really look at it, if you had to really transport the 16-bit IQ, this is the lowest possible 8-bit I and 8-bit Q. Typically, it will be 16-bit I, 16-bit Q. Of course, with the compression, you can reduce. You essentially will get into 23-bit of IQ traffic, and of course, on top of that, there will be additional control information as well as the management. So, effectively, a 25 gig barely can handle this information when you get into this 88R configuration. Now think of the 64TR system that Dr. Budiraja talked about. If you have to have 64 antenna stream to be transported, this transport capacity is not good enough. So how do you really deal with this? This is where category B radios come up, where the if the only 8 layer is being handled even for 64TR, you potentially could transport that information and then apply the compression and somehow fit into the 25 gig interface. Otherwise, you'll need multiple of them. Now, as the high-speed interfaces increase to just the transport the data because of this disaggregation, it brings in the additional challenges both on synchronization as well as the energy management. So next, I will quickly talk about what are some of the challenges. So if you really look at some of the aspects, the multi-vendor interoperability, that was the primary objective. However, have we really solved that problem? So in that context, I will give one example on the integrity of information in a decoupled architecture. I'll get into little bit of details and food for thought in the next slide. So one of the thing is, how do I synchronize the control and data between the DU and RU over the open frontal interface? There are definition of the delay profiles, and there are different methods of computing the delay profiles, whether it is statically configured or it is dynamically discovered based on the distance between DU and RU on the optical fiber, then the internal processing time of RU, and the synchronization at the antenna interface, which is 3GPP stated requirement for the airframe synchronization. And how do you make sure that 65 nanosecond of timing error alignment is done? Next is the energy efficiency. So as we split the interfaces, there are need for additional processing to make sure that the interoperability can be done. So that adds to the energy efficiency problem. So how do you really compensate for that? By doing a cross-layer optimization using the intelligence that otherwise was not possible. So antenna calibration is the other thing. I'm sure Dr. Budiraja, you will have a lot to learn because massive MIMO has been done in the IIT test bed, but this is something that we are really struggling to figure out. Precoding and beamforming, of course, there are multiple challenges. If you have to get into CAT B, CAT A, the DU vendors do it in a particular way, and when we are trying to interoperate with them, there are challenges. Security, as you look at the IQ symbol, currently is unencrypted, and if you want to encrypt, there will be energy consumption need will so there are multiple challenges to be solved. So the question is, this is just an example. You can see that TX window, RX window coordination from when you transmit the information from the ODU and when it gets into airframe where DLUL has to have a fixed timing relationship aligning with the timing error as per the 3GPP physical layer specification, it's a daunting task, right? So how do you really make sure that this interoperability is ensured considering the DU vendor has implemented it in a way, and we are trying to implement our way, and somehow make sure they can interoperate. So this is where we are. And moving forward, what I think will be really helping this ecosystem, if we have to make this open run, this disaggregated network elements to succeed, is the opening regional interop test bed. Open run has done multiple plugfest mechanisms, but I think regional interop test bed where all the suppliers are willing to come together to the interop definitely will be helpful. We as an RU maker, of course, we would like to interoperate with all the DO providers, and then make sure that it becomes really open. And that way, we I think we'll be able to discover new issues that is not addressed in the standard today, and evolve the standard to address these practical issues. And of course, this becomes a great way to validate any new innovation that we do in the product, for example, energy management and related stuff, right? So with that, I will very quickly pause and stop my session, because we are little over time. So thank you very much. I hurried a bit just to be on time. So really appreciate all of you speaking in the session and enlightening us with all the information that you shared. Thank you very much.
Chair, there's a question mentioned in the chat box.
Yeah,
I'd like to request Asif to flash it.
please. Which split is best suitable for this wireless front hauling? I think Bomkesh, this is already standardized. The answer is yes. For transporting EC3, front haul standard is being used. So if you go to Open Run, it is openly available. There is a document called CAS, that is control user synchronization plane specification. I think the latest one is release 10, version 10. And there is a corresponding open front haul specification called the M plane specification. So then there is for ORAN related open orchestration, there is an ORAN interface. So just go to the oran.org, look for these documents. If you cannot find, I'll be very happy to assist you.
Thank you, Chair, for addressing the question. Now, I would like to request you and Mr. Anand Sampatraman to say a few words for the closing address of this session. And followed by this, we'll have a concluding session for the whole conference. Thank you.
Thank you, Anand. I would request you to convey a vote of thanks for the speakers.
Thank you, Mr. Subhash. First of all, my thanks starts with you. Thanks for the great comparing of the session, and your final session was simply great. I definitely had interesting interpretations from what you said. Having said that, thanks, Mr. Guilio, Mr. Atul Kumar, Mr. Satish, Mr. Narayanan, Mr. Rohit. Thank you all for the session. Thank you, Akash and Asif. Thanks for all your support. Thanks, Mr. Vijay Madan, Ms. Bindu, for all your support to make this happen. On behalf of TSDSI, thank you all. Thanks all attendees. I think we had more than 40 participants during the session. Thank you all for taking time, and hope to progress on the subject with all your support. Thank you.